Welcome, everyone. Good evening to everybody on the East Coast, late afternoon for everybody on the West. And I hope all of you are doing well. Welcome to another of the ACE Talks. Today, we are very lucky to have Troy Acromano from Texas A&M. And before I introduce him, I'll just introduce myself and about ACE. So I'm Peetak Mitra, and I'm a PhD student at the University of Massachusetts Amherst, and I am the stream owner for the machine learning and climate science stream. So ACE is a community of machine learning practitioners and researchers who have gathered around topics in AI research, engineering, and products. We host free live sessions like this 3 to 5 times a week. You are highly encouraged to look at our website, to look at upcoming talks and the subject areas. Please make sure you subscribe to our YouTube channel, ML Papers Explained, to access some of these videos. And we currently have about 14 streams, and more information on that is on our website. And these streams are focused on various ML topics. And this session is from the machine learning in climate climate stream. Hope you enjoy it and you come back. So now I'll student at Texas A&M University. He graduated from the University of Maryland with a Bachelor's of Science in Atmospheric Science and a minor in physics. He has been part of and has completed successful internships at 2 weather modeling centers, National Center for Environmental Prediction, NCEP, and the Naval Research Laboratory, NRL. He has been working on a machine learning weather forecast modeling for a little over a year. Troy will primarily talk about his work published in the prestigious Geophysical Research Letters titled A Machine Learning-Based Global Atmospheric Forecast Model. Thank you so much for joining us, Troy. The floor is all yours.
Thank you for that very warm introduction, and good evening to everybody, or good afternoon. I'm really excited to give this presentation. I've been working on this research for almost a year and a half. It really was a big collaborative effort. So before I start, I'd just like to thank my collaborators, Dr. Isman Soon-Young, Dr. Brian Hunt, Dr. Ed Ott, Alex Winkner, and Dr. JD Peetak. And as mentioned, I'm going to be talking about a machine learning-based global atmospheric forecast model. And I believe there's going to be a link to this, but if not, there's also a link to the paper through GRL at the bottom of this title slide. And with that, just a brief introduction. So as many of you all know, machine learning, or ML, has a wide range of applications, from image classification to playing complex human games such as Go, to language processing, understanding what sentences mean, and language sentiment. Machine learning spans almost every field of in science, so it's no surprise that previous work has showed that there can be machine learning algorithms that successfully imitate and predict complex spatial temporal systems. These systems are usually on the small scale when in this previous work, but some of them go all the way to predicting how fires propagate through the forest and such. One of the biggest spatial temporal chaotic systems that affects your life every single day is the weather. It is quite chaotic, complicated, and weather prediction is really a multi-billion-dollar business. Weather can affect from trivial things like whether you need an umbrella to walk outside, all the way to devastation on the order of billions of dollars. And that's not even including death tolls and the effects on the people who are devastated by disasters such as hurricanes, droughts, and floods. So being able to predict the weather is really important. It's no surprise that numerical weather prediction, or NWP, which is the use of computational numerical calculations. These are, fluid simulations of the atmosphere that predict the weather into the future. These models are quite complex. Almost every country including the United States, runs a weather model. The United States actually runs multiple weather models. That's how important this is for things like aviation. It affects the economy. There's large trades that go because of whether these models are going to predict a drought in 6 months or more rain for crops over the Midwest. So these models are a multi-billion-dollar industry. So there's been quite an advance of
Troy?
Improving these. Yes, can you hear me?
Sorry. Yeah, we can hear you fine. It's just that your slide deck is not moving. I'm not sure if you're actually moving through your slide deck.
Okay, no, this is still my introduction.
Okay, sorry.
Yeah, sorry.
That's okay.
You scared me for a second. Yeah. So numerical weather prediction is quite important, and machine learning has really taken a hold in weather prediction, but machine learning really hasn't been able to forecast the weather. Given a set of initial conditions, no machine learning algorithm has been able to satisfy these requirements that we came up with when we wanted to make a global machine learning only forecast model. So we came up with a simple 3 bullet points worth of things that the global model would need to, or global machine learning model would need to satisfy in order to be called a forecast model. The first one's quite simple. Is it computationally feasible to train? I can write on paper a machine learning algorithm that would be able to possibly emulate the atmosphere, but if it's going to take 3 years on the world's largest supercomputer to train because it has billions of tunable parameters, that's not computationally feasible as of now. However, if it takes 2 days on a few GPUs, that's quite computationally feasible, and that's really, a good application. This is an interesting thing because every year supercomputers get larger, there's more technological advances, computer software gets faster. So this is a moving, target, and we want to stay up with being able to take advantage of these pre-existing high performance computers. So we ended up actually making a very scalable machine learning algorithm that satisfies this requirement and also is able to leverage these high performance computing centers. The second thing is, if you can train this machine learning algorithm, can it predict 3-dimensional atmospheric variables for the entire globe? This is quite complex. There's a number of different variables that you need to predict for a forecast model. Temperature is quite important because you want to know if you need shorts or you want to put the jeans on today. But things like weather are really important for aviation. If you have a crosswind at the airport, you're going to want to have planes have more fuel so that if the winds are too strong, they can circle for a while. Moisture is really important variable if you're interested in precip, which almost every farmer is very interested in, if it's going to rain tomorrow or if it's not going to rain tomorrow. And then there's even a plethora of more variables that need to be predicted from a global forecast model. And this gets even more complicated. Temperature, wind, and moisture are not independent of each other. Temperature is driven by changes in wind. Moisture is affected by wind. Wind can be partly driven from temperature, and these are all non-linear. So this machine learning algorithm is going to have to be robust enough to understand and learn how these variables interact with each other. And doing this on a globe even presents more problems. If you want to take your neural network and try to represent the globe, which is a 3-dimensional globe, as a 1-dimensional vector, that poses a different set of problems because areas in the poles have much different geographical, in the X and Y space. They're much different in how far away one latitude is from another latitude, and the neural network is going to have to understand that. Also, things like how weather over the ocean and weather over land can be completely different, even though they're very close to each other geographically. So the machine learning algorithm is going to have to incorporate and be able to do that. So it has to be versatile and quite flexible. And then finally, if you can train it and it's able to do that, can it produce realistic atmospheric motions and phenomena for a sufficient amount of time? Being able to predict 1 hour into the future is quite an achievement for machine learning, but it really doesn't benefit people who want to learn, or people want to be able to predict what the weather is going to be like next week. So it's going to have to be able to produce realistic atmospheric motions and phenomena, but be able to go out at least 5 days. Most weather models that are run operationally and used to make forecasts and decisions run out to 2 weeks. This is about the practical predictability limit for state-of-the-art models because of the chaotic nature of the atmosphere. However, if your application is climate, that's a much different story. Climate models run for centuries. If you want to know what the atmosphere is going to look like at the end of the 21st century, you have to be able to start with the conditions that are right now and present and integrate your model for almost a century. And sometimes you need to even go beyond that if you want to do things like what was the weather in the 1400s for things like hindcast. So if you want to use a machine learning algorithm to do climate simulations and emulate climate, that's even more problem because you have things like conservation of mass and energy as well as conservation of moisture in the Earth system. So none of these requirements are easy, but going down, they each get progressively harder. So in order to say that we have a global machine learning forecast, we wanted to at least get 1, 2, and 3 of this. There could be, you can come up with a more rigorous definition, but this was where we started, and that's how we designed our algorithm. So we wanted to use something very robust, something that was computationally feasible in the modern high performance computing environment. Yes.
Sorry to interrupt you again. Are you still on slide 1?
No, I'm not on slide 1.
Okay, so we're still on slide 1. So can you just make it full screen or maybe try to reshare again?
Oh, no, I'm so sorry.
No, it's okay. Okay.
Can you see this?
Yes, I can. Yes, it's in slide 2, slide 4. Yep.
Yeah.
Okay.
Does that work?
Yes, I'm looking at slide 4 now.
Oh, I'm so sorry. I didn't realize.
No, it's okay. No, it's okay. Perfect. This is good.
Okay. So this was the slide pertaining to the requirements. Sorry. Now going back to this. So we wanted to have a machine learning algorithm that was robust enough to handle the part where we were talking about needing to understand the differences between the variables, differences in the land and ocean and such. So we chose reservoir computing. Reservoir computing is one of the many different machine learning algorithms. It dates back past even 2009 with Jaeger in 2000. The most important about reservoir computing is it's not deep learning. It was the first successful attempt at a recurrent neural network architecture that was computationally feasible a decade ago. And because of this, it's still very computationally effective compared to the state-of-the-art recurrent neural networks, such as long short-term memory networks and even more advanced things like gated recurrent units. So we have this algorithm that can be trained on the order of 10 to 100 times faster than these state-of-the-art recurrent neural networks. Because this isn't recurrent neural network, it's going to have memory. Previous attempts at making a global machine learning forecast model tried to use convolutional neural networks. So this is where we set ourselves apart from the other attempts. And really, we think this is an advantage. Being able to have memory in the network allows for things like the weather 2 hours ago to affect the weather today instead of presenting weather as a image processing and classification problem, we're presenting this as a time series problem. And this really helps, being able to get phenomena such as the diurnal cycle. So as the sun comes up, the land's going to heat. You're going to have this, almost sinusoidal function in your temperature. And as the sun goes down, you start losing heat. Temperature drops. If you just try to look at the Earth as a, pure image classification from 1 hour to the next hour, you might not capture these very subtle features like that. And there's many different oscillatory functions in the atmosphere, like atmospheric tidal waves and such. So being able to have a time series, treating this as a time series problem really has quite an advantage. And most importantly, the other important thing about a reservoir computing is previous studies have showed that reservoir computing has comparable performance in low dimensional spatial temporal chaotic systems. So we have a more efficient architecture with the performance of a state-of-the-art recurrent neural network. So it really was a no-brainer to base this entire algorithm around reservoir computing. For those who have never seen reservoir computing, it's actually much more simple than some of the state-of-the-art long short-term memory or gated recurrent unit architectures. Really, it just is broken up into about 4 parts. You have your input signal, because we're treating this as a time series problem. You have your U of t, so it varies with t. You have this input layer, which we call Win. This is a static matrix, so this is a static random matrix. There's no training that goes on during this, so these are all fixed. So when you start this, reservoir computing program, you just get a random matrix. This stays that way, and this helps couple your input signal to your reservoir dimension. So the reservoir is going to be much higher dimension than your U of t, so you're going to need a way to couple that signal to reservoir space. The reservoir is quite interesting. We call it the reservoir layer. this ends up being a low degree directed random network of d number of nodes. You don't have to do this. There's quite a number of different approaches. This is just the way we chose because it's really easy, and it also takes advantage of things like sparse linear algebra. So we can represent this random network as a graph and use an adjacency matrix that's very sparse, and because it's so sparse, it makes the computations much easier. And a lot of these packages that we use are very highly tuned, so we get really great training speed out of that. But reservoir computing offers a couple of interesting things. You can use a reservoir as actually a physical device. There's a lot of work that's gone into using things like a fishbowl of water as a reservoir. I won't explain how that's possible, but I highly recommend looking how they do it. They, I think, shoot lasers through it and use that as a non-linear dynamic system, and it's really interesting. So we think reservoir computing is, even though it's not the most popular method, is still going to be very prevalent into the future, and it's very versatile, as I mentioned. And then finally, you have your last layer. So this is your output layer. This is where the training actually takes place. This is where there's tunable parameters, and this maps your reservoir state, your higher reservoir state, back to your signal space. So it ends up being actually a really simple system to solve, where you want to put U of t in, your W in maps from a low dimensional U of t to a much higher dimensional reservoir. The reservoir has these nonlinear dynamics. There's memory in the reservoir. These nodes are randomly connected. They connect to themselves. So just like it is a implementation of the recurrent neural network. And then we take this state and we map it back into signal space. Now we do something special here. We don't want to get that. We put U in at t, but we want to get something out that resembles U of t plus delta t, so we can actually make a prediction. And we train the reservoir system to make a one-time step prediction into the future. So we end up regressing towards U t plus delta t, and that's all great. We can make we can make a one-time step prediction. But as I said, the bullet point that I wanted to talk about was having something that can predict X amount into the future. So if we want to predict weather, we need to be able to predict 2 weeks into the future at minimum. So being able to predict 1 hour is fine, but we're really not doing anything in terms of satisfying that last criteria. So here's where we do something interesting. So during the training, which is we put U of t in, the machine learning, which is represented as this blue box, not the stereotypical black box that some people call machine learning, but and then we get a U of out at t plus delta t, and that's during the training. Once all the training's done, we now have this trained machine learning network that is able to make one-time step into the future. So if we want to start making predictions at time t, we train it up to time t minus 1. We cut it off. No more data is getting inputted. The machine learning is, the system is solved, and then we have a machine learning that can predict into the future. We put then t into the machine learning network, and we get t plus delta t. So this is a prediction into the future, and we have one-time step. So in our case, it's a 1 hour prediction into the future. Then, yes.
So we have a question already from one of our attendees, Jody Frank is asking, before we move on from the reservoir computing, I think this is relevant here. So okay. Jody is asking, does reinforcement learning pale in comparison to reservoir computing? The setup seems a bit similar for using a gradient boosting model with regards to using a sparse matrix. So what are your thoughts on that?
Okay. So in terms of reinforced learning, there's definitely similarities. I'm sure when Jaeger was designing the reservoir computing, and because this was around the same time that reinforcement learning was starting to be introduced, I'm sure there's very similar, they shared methodologies and such, but I think this differs a little from reinforced learning. Really, I would say it's definitely a different application. Reservoir computing, I would say, is, pretty far from reinforced learning in terms of, we see the applications of reservoir computing for, but we've never tried reinforced learning with such problem. Again, we're still trying to treat this as like, a time series problem.
Sure.
And I feel that the, usage of reinforced learning is especially when you're trying to do it like in an unsupervised way or something like that. A little different than this, but that's a very good question. I think the math is actually very close to each other if I remember my machine learning classes correctly. But
So just to before we move on, I just had this question about this reservoir computing. It seems very interesting, and you say that there are only one set of trainable parameters. Is that right? The W out.
yeah, so that it's not one like parameter, but I mean
Sure.
it's not like your stereotypical convolutional neural network like where you have multiple hidden layers and each one of those in each one of those layers you have tunable parameters, and you can use backward propagation to do that and forward propagation solving methods to do that. In this case, it's really just one layer that's trained. So it's really
And how
just
is it trained using like backprop? Like
no, actually, if you formulate the problem correctly, it ends up being a very simple matrix inversion. So you can use something
Ah,
like a linear least squared solver. You can make it a more complex problem, but for the algorithm that we use, it's very simple in terms of just using a linear least squared
interesting.
yeah solver, and that's how we get these great, as I mentioned one slide ago, we're getting 10 to 100 times faster training than that of something that needs backwards propagation, because an LSTM needs backwards propagation method.
Sure.
There's definitely ways to boost that and make it quicker, but really nothing is easier than solving a linear
Just doing,
system.
yeah.
Yeah,
True. This, yeah.
so that's really a big advantage here, and we would never have done this had it not been shown that reservoir computing could get comparable results. If a gated recurrent unit said it was doing much better at a time series of chaotic system that is treated as a time series, then we would have been doing that. But we chose reservoir computing, and the next part of the architecture that I'm going to explain is really independent of the reservoir. You could use something like a convolutional neural network, a different flavor of recurrent neural network. Really, the algorithm is pretty independent of that. We chose reservoir computing for the convenience and speed.
Cool. Thank you. Thank you so much.
So thank you for the good questions. Okay, sorry. Going back to this slide. So we trained our neural network. We are able to predict one time step into the future, and we want to make an iterative process. So we take the last trainable data, we put it through the machine learning algorithm, we get a 1 hour prediction, and then we feed that back into it. Because the machine learning algorithm learns to take U of t and just make a 1 hour prediction, it doesn't matter that now we took a already 1 hour prediction and we put it back in, so we get a 2 hour prediction. And we can take that 2 hour prediction, get a 3 hour prediction, or 3 time step prediction, and you kind of see the picture. Now we have an iterative method that satisfies our last requirement. As long as it produces realistic phenomena, the bullet point 3 with being able to make a prediction arbitrarily into the future is satisfied. And this really offers a lot of, convenience, because no one person wants just a one forecast. So if you want a 5-day forecast, you could train a machine learning neural network. You can train a convolutional neural network that doesn't have an iterative process in it to predict a 5-day forecast, but you're losing a lot of details. You're not going to be able to make a 3-day forecast. You'd have to train another convolutional neural network or a recurrent neural network to do a 3-day forecast. If you wanted a 1-day forecast, you'd have to train another. So this iterative method really helps, and it's at the core of numerical weather prediction. No one has a model that can train that, no one has a weather model that just predicts 5 days in the future. It predicts every few seconds, and then you look at the day 5 if you're interested in day 5. If you want to know what the weather is going to be in an hour, you look at that. So this is really getting closer to the core concepts of what numerical weather prediction is, and it's purely data driven, which is quite interesting. But as I mentioned, atmospheric numerical weather prediction is quite complicated. They are some of the most advanced code and require some of the most advanced supercomputers because of these memory requirements. The atmosphere can be represented at very high resolutions, and at each resolution, at each grid point, you need to represent the full 3-dimensional atmosphere. Most numerical models have 60 to 100 vertical layers spanning from the surface all the way up to the mesosphere, because there's applications for weather in the mesosphere if you're interested in things like aurora forecasts or how satellite communication is going to work. And if you're at the surface, obviously that's where we live, so we're very interested in what the surface looks like. And there's correlations between the two. The weather at the level that planes fly directly affects the weather here at the surface. So we need to be able to represent that, and that requires a different machine learning architecture than what we're usually used to. No machine learning algorithm could take in millions of inputs and give out millions of outputs and make a reasonable prediction, at least in this day and age. In 20 years, when supercomputers are, 10, 20, or 30 times faster, than maybe that would be able to be satisfied our computationally feasible requirement. But as of now, no machine learning algorithm is able to satisfy our requirement that it would be computationally feasible. So what we do is we break the globe into a bunch of small pieces. So instead of one reservoir computer to predict the entire globe, one reservoir computer predicts a very tiny subset of the globe. So this picture illustrates what I'm talking about. So each one of these blue boxes, there's 9 of them, represents one reservoir, and these can be trained independently too. So if you have thousands of cores on your supercomputer, you can train each one of these blue boxes independently. So this is massively parallel. The code really scales nicely, even in the thousands to tens of thousands of processors. That's what we're using right now. This is an example of what the globe would look like at a specific resolution of 3.6 degrees by each grid point 3.6 degrees, represented on like a Latin long grid, separate from each other. So it's a pretty coarse resolution. It ends up being like a 200 kilometer between each one. These are pretty close to a typical climate model that you would be interested in at this resolution.
So Troy, I have a question.
Yes, of course.
It seems very similar to the self-organizing maps kind of approach.
Yes, like SOMs.
Yeah.
We really took, so SOMs are definitely in, like, again, a different application, but it's the same idea that we use here. We definitely leveraged a bunch of, machine learning architectures to try to come up with the one that worked. It's a little different than SOMs, especially because they're self-organizing, and they actually have a really great use in atmospheric science, but it is a very similar idea. And I mean, this is almost a similar idea as a convolutional neural network, where you want to get the convolutions, as that's really what's important. And as you go down into your hidden layers, you get more and more information extracted from your image, and it can be represented by smaller and smaller, data, or smaller like convolutional dimension. So we took these ideas, and it's called locality. That's how, that's what we call it in data assimilation and machine and numerical weather prediction. It's like this principle of locality. If, for example, on this map, this data point here it would be impossible for it to affect this data point right here in a span of a few seconds, because there's no wave that can travel fast enough in the atmosphere to affect this. So we use this principle of locality and to reduce the dimensionality of the problem. So it really is like this architecture really is just taking the ideas from a bunch of different things, such as like a convolutional neural network, a SOM, and even self-organ and the other architecture that was the question before. So they are definitely different, but the idea is very similar. Again, because we're treating this as a time series like problem. Is that good?
Oh yeah, perfect.
Okay.
Perfect.
I just want to make sure you're. Yeah.
Sorry, I was muted. Sorry.
Oh, no worries.
Yeah,
so
keep going.
Okay. So again, we're using this principle of locality that I just mentioned to reduce the dimensionality of the problem and be able to scale this to be massively parallel on high performance computing centers. So because information, as I've just mentioned, and that can't travel faster than the fastest wave in the atmosphere, we can reduce these regions to be quite small as long as we use a fast enough time step. The data that we use for training is quite limiting. There's nothing faster than an hour in terms of temporal resolution for real data that represents the best guess for the atmosphere in the past. So we're really limited by an hour, and we're limited by the memory constraints and how much data we can really fit on into these like small reservoirs or these small geographical subregions. So we end up getting a map that looks very similar, that looks like this when we put it into a Latin long grid. Each reservoir that's trained independently only has to predict 4 grid points. At each one of these grid points, there is a full 3-dimensional vector of the atmosphere. You have your variables that you want to predict at each height level, and you have multiple height levels that expand from the surface all the way up to as high as you want. But if you did this without the red line, you would get information, you wouldn't have any information to pass. So the red line here is the key to how to make this parallel machine learning architecture work. The red line represents what we call overlap. So the red line is the overlap for the information that gets put into our neural network, our reservoir computing network for this one specific blue box. So the blue box in the middle has 8 neighboring regions. And when we are doing the training, we put more information into our reservoir than what it predicts. So it predicts this small 2x2 square, but it gets information from its surrounding 8 geographical regions. So during prediction, it's able to understand how information from here affects this grid point, how information here affects that grid point, and etc. But this also gives us really great flexibility when we do the prediction. When we do prediction, information can pass seamlessly from the neighboring 8 regions into this, and then if you imagine, I don't have all the red lines here because this plot would get quite ugly very quickly, but you would have overlap here. So each one of these, blue boxes has information from the 8 neighboring regions. The only exception is at the poles, where we don't have any data beyond the poles. So that the picture looks a little different, but the idea is still the same. Information can flow from one region to another when we're doing prediction. And this is really the key to this whole architecture working. Without this, you would get results that don't look realistic. You wouldn't be able to resolve large scale waves, but because we keep the time scale small enough so that information never passes from here all the way to here, which is very similar to when you do fluid dynamics, the CFD condition, where you can't have information passing during one time step outside of your grid spacing. If the information went from here to here, it would bypass this, and that's a very simple explanation, but it's the same principle here that we're using. So the training data. So we acquired all the possible training data for the ERA5 reanalysis data set. So ERA5 or ERA5 is the most sophisticated reanalysis data set that is in existence right now. Reanalysis data is probably a little more different than what most people who do machine learning are used to. This is not a perfect data set. It's impossible with our current setup to get a 100% realistic representation of the atmosphere. The observations are very sparse in time and space. There's very large differences because of orography from one observation that might be 1 kilometer away from another observation. So we have to use things like data assimilation to fill in the gaps to get a very homogeneous data set. So something that is spaced regularly, because the real data is not spaced regularly in both time and space. So that's what I mean by reanalysis data. But that's as best as we can get. There's no better training data for something that would need a homogeneous grid like our machine learning algorithm. And we regrid this data to a climate model, horizontal and vertical grid. This is done for a number of reasons. Because we want to compare this directly with the climate model to see how well our machine learning does compared to a climate model. We want to be it on the exact same grid. It also, which I'll allude to in a couple of slides, is another project and the next step for this project. So having it on the same grid is quite important. The variables that we choose for our prognostic variables for our machine learning algorithm are the 2 components of the wind. This is called U and V. That's how I'll mention it. These are very important for a number of applications. Temperature, the thing that we feel every day when we walk outside. Here in Texas, it's like 100 degrees. So it's quite important to know when I can actually go outside and walk the dog. So that's a very important variable. Specific humidity is a moisture variable. So this is where we get things like clouds, precip and stuff. We need to know where the moisture is in the atmosphere. And then finally, we need something called surface pressure. This is just the pressure that follows the terrain. So this is literally the pressure at the surface. This is a little different than the other variables because one, it's a two-dimensional variable and it's a terrain following variable. The other ones are set at a specific height above, so they're not terrain following per se. So it's a little more interesting of a variable. And because of data requirements and memory problems, we really limit ourselves to 20 years of data for training from 1981 to 2000. And we use 19 of the years for training and 1 year for verification. The reservoir computing really doesn't have that many hyperparameters, so there's not a validation window that we need. So don't be scared when you don't see a validation. There are some hyperparameters, but the way we do it in parallel, it's really impossible for, as of now, for us to change these hyperparameters other than really intuition and guess, because we have so many different reservoirs, all of which are independent of each other and may or may not need different hyperparameters. But the hyperparameters we chose seem to fit quite well for machine learning. So we train it for 19 years, and we had we threw thousands of processors at it. So we have each reservoir only predicting a small subset. Let's see if it produces atmospheric, realistic atmospheric variables. So I'm going to show is a movie from a forecast. This is, again, purely a machine learning driven, forecast, and we're going to run this out for 14 days, I believe. So what's plotted here is near surface temperature in Kelvin, and the wind vector is also plotted for the near surface. So this will help us see things like cyclones and anticyclones. You'll even see a tropical storm, I believe, that starts off the coast of Japan and move up through this film, all of which, again, are purely predicted by a data-driven machine learning algorithm. And it should be noted that this machine learning algorithm has more than one layer. I just chose to choose the near surface one because this is where I believe is easiest to represent and what would be easiest for the general population to, understand. So I'm going to let the movie play, and we're going to see a number of things. We're going to see things like the diurnal cycle. So we see this, 24-hour period cycle where things get warmer and then cooler at night, and we see that because this is on a globe, the sun doesn't rise, uniformly. It starts over in the east and moves west in this plot. So somewhere near the North American continent, moving this way, we see that. And again, none of this is explicitly told. Machine learning, because we're treating it as a time series problem, is able to understand this. We see things that are much larger than our geographical region. So each one of these wind vectors represents just one grid point of the model. So a 4x4 is really only this big, but we see large scale features like this very large extratropical cyclone south of Alaska. We see things like warm air moving with the thing. So, because the wind is going to help advect the temperature, we see wind moving. We see the wind at the surface moving the warm air from the equator towards the cooler air. And then we see on the back side of this cyclone where winds are coming from the polar regions to the equatorial regions, we see cold air following. And again, none of this was explicitly told. It all was just made from pure machine learning. There's no, conservation laws that were built into this. And we're really quite pleased with this result. And again, this was stable. So we started, if we start this movie again, from January 27th to February 13th. I think it ends on February 13th at 0. So we are getting stable, realistic results. That doesn't say that the 12-day forecast or 14-day forecast has any skill, but this satisfies our requirements that we're getting stable results out to 2 weeks at least. And we don't see any large systematic loss of energy and stuff. By the time we start reaching day 20 and stuff, there seems to be some loss of moisture and such. But again, there's no conservation built in to this model. So it's really doing a remarkable job. And again,
Troy?
Yes.
So we have a question from one of our audiences. Iki Ruiz is asking, how granular is the data set resolution-wise? Days or hours or minutes into 20 years? Like you said, you have 20 years of data. So how granular is that resolution?
It's quite granular for our first attempt. Again, we're limited by how many processors and time we can sit on the supercomputer, but this is the full resolution. So each one of these, wind vectors represents this. This is I think it's 3.6 degrees of latitude and longitude separated. So at the equator, it's, it ends up being quite a large distance. I think it's 300 kilometers between each one of these grid points, but in the extratropics and up there, it's about 200 kilometers. And once you get to the poles, it's very tight, but
and what is the temporal resolution? Is it like
it's 1
hours?
hour. So 1 hour is the highest temporal resolution that is offered in the AIR5 data set. So if your machine learning algorithm needs something faster than that, it's unfortunately not possible to do during this time. So that's why we really needed something so robust.
Perfect. Thank you.
Oh, no problem. But before I move on, I mean, I really like to hammer this point that, we really see realistic atmospheric, phenomena here. We have, so during the winter months, so this is February, this is winter in the Northern Hemisphere, there's a current in the ocean that comes off of the Japan coast. It's called the Kuroshima current and follows, you can almost see it, and the temperature follows out to here, and then there's the extension region. This is quite a common place to see large extratropical storms, and we see a large extratropical storm that's developed, and because we're so far away from our initial conditions, the machine learning algorithm is not just simply advecting or anything, it's truly understanding the dynamics. We see things like cold fronts and warm fronts that develop in this. And then here we see another extratropical cyclone moving off the coast of Japan and moving towards the Alaskan coast. This is a very typical track. So it's not only able to take the initial conditions, make a few days forecast, but it's understanding the climatology too. If it was throwing, very large high pressure systems over Hawaii and stuff, then we would be thinking that, it doesn't understand climate, but it seems to really capture the climate too. We see here at the end of this a very large, powerful extratropical cyclone with winds starting over the, tundra in Russia coming down here. We see the changes in the temperature fields that would be expected with such an extratropical cyclone. And again, all of this is captured just from a pure data-driven perspective. Oh, sorry. Let me see if I can change slides. Yeah, it's great that it can make a great movie, but what is the error? How skillful is the forecast? So we come up with a couple of criteria for how skillful the forecast is. One is, can it beat persistence? Persistence is, was one of the most important variables when people started numerical weather prediction. Persistence just means the forecast at time 0 will be the weather at forecast time t. So nothing changes. And if you can't beat persistence, you really are doing quite bad. That means your model is horrible in that case. But we are able to beat persistence, which is good. The other criteria is climatology. Now, you would think that climatology would be an easier variable to beat, but actually climatology ends up being the hardest variable. No model can beat climatology forever. Climatology is a really powerful thing to be able to beat, especially once you start getting away from day 1 and day 2 forecasts. If you're still beating climatology by day 3, 4, and 5, that shows that your model has at least some skill. So those are the two benchmarks in terms of that. And then we also ran a numerical model. So because we're on the exact same grid as this numerical model, which in this figure is speedy, which is the green line, we can directly compare at each pressure level what the variable was and compute, a global root mean squared error. We can do in regions and stuff and see how well it does compared to a numerical model. And what we see is quite remarkable. For the first 24 hours, our numerical model is doing on par to a little worse than our machine learning. That means our machine learning is beating a numerical model, especially in areas that the numerical model struggles, like the stratosphere. The stratosphere is a little more complicated than the troposphere, and this model seems to be struggling with that. So we see that we're doing on par for a 24-hour forecast. If we move to day 2, the machine learning algorithm starts to degrade a little, but we're still, again, doing on par with our numerical model. We're still beating persistence at all levels, and we're definitely still beating climatology. But we see that the climatology line starts creeping in by day 3. Persistence is no longer the metric that we want to beat. We want to beat climatology, and we are still beating climatology. This is averaged over that entire year of verification. So this is 2000. We ran a simulation every 2 days. So so this is averaged over 176 different forecasts. It ends up being quite a large amount of data. So our supercomputer was not happy with all of this data sitting on there. But again, even by day 3, some areas were doing better than the numerical model, but some areas were still doing worse. And we're still beating the numerical model by quite a bit in the stratosphere, the area where I would say the numerical model struggles the best or struggles the worst. And this is for temperature. If we move to something like the V component of the wind, so this is your north-south component of the wind, this is a great proxy to see how well your model is capturing wave dynamics. And this is where the numerical model does quite well. The model is highly tuned to understand the different wave structures in the atmosphere, such as Rossby waves, gravity waves. So no surprise that our machine learning or our data-driven only model struggles, but it still does quite remarkably well. For the first day, it's doing on par or just a little worse than our numerical model, but still beating persistence in climatology and by a factor of like 2 over here. By day 2, we see that the machine learning model is doing worse than our numerical model, but still has skill. We're definitely beating climatology and persistence, but by day 3, we're really just doing as good as climatology, which means our forecast model really only has skill for the V component of the wind out to day 3. We actually think we understand why this is a problem, and I would love to talk about it if anybody's interested offline, but we think there may be a solution to extend this out even to day 5, day 6, and 7. It just doesn't capture the long waves correctly, so the error starts saturating at very long waves very quickly, which degrades the results. And then finally, we look at moisture. So this is our specific humidity variable. This is the moisture variables I mentioned. These are driven by subgrid processes on the numerical model, like cloud formation and such. So the numerical model really struggles with moisture, especially for the first few days. It captures the climate of the model. It's not even able to capture the climate correctly because moisture is such a hard variable to predict for climate simulations, especially at the resolution we're talking about. But our machine learning model has no problem because it's a pure data driven. It doesn't need to have things like parameterization and stuff. It's just learning directly from reanalysis data. It excels really in the first day, beating persistence, beating our numerical model, and really beating climatology. We see that it even understands things like boundary layers. So where the error is the highest is actually not at the surface, but right above the surface. These things are driven by, cumulus clouds, convection, which the model, again, really struggles with because of the resolution that the models run at. But the machine learning model is still able to do that. And we see by day 2, it's still beating all of our criteria. And by day 3, we start losing to climatology, but still doing better than the numerical model. And our tiny, surface layer, which is right here, is just doing about on par with climatology. So we have about a day and a half, 3-day prediction skill with the moisture variable, but still at every time is doing better than our numerical model. But there are limitations to the machine learning only model. I'd like to say that it was perfect, but obviously it's not. There's a couple of things that are, limiting. There's no cross-polar flow. So the way we designed our grid, information can't flow from the North Pole moving in the direction. If you can wrap your mind, sitting at the North Pole, everything is always to your south. So there's a singularity at that point, and that's been able to fix that, but we think we understand how to do that. An easy way is actually to represent the Earth as not as a sphere, but as a cubed sphere. That's how some numerical models actually do it. That's an easy fix. The other thing is the cost function used to train doesn't have any physical constraints such as global conservation of energy and tracers. We're making great strides on trying to incorporate this into our linearly squareds. We think we have possibly a solution, but we haven't tried it on this full, global forecast model. We're going to try it on our easier to run tests. And the horizontal resolution, I think this is the biggest caveat, is considerably lower than that of a state-of-the-art numerical model. We aren't even close to running the simulation at what a numerical model that would predict, your weather that you get on your Weather Channel app or your so we're still quite a bit away from that, but this was our starting point. And finally, errors saturate too high. There's too much variability in the long wave dynamics, and this leads to not capturing the climate perfectly. So here we are looking at a time series of a prediction from our numerical model: green, which is speedy; black, which is climatology; red, which is persistence, again saying that the state of the atmosphere at time 0 will be the state of the atmosphere at time t; and our numerical model, which is in blue. And we see for the first one day we're doing better than the numerical model, but we're doing always worse than the numerical model after that. And the numerical model hasn't even reached saturation by day 10, but our machine learning has reached what we call saturation, or when we pass persistence, at day 4.5. So we still have quite a bit of work to do, but it seems that it reaches a stable, we see the errors saturate quite well, just not at the appropriate level. And that's probably because of things like conservation laws and not being able to see these very, very long waves. We're not so sure exactly why. And then finally, I just want to talk about our next step, where we're going. I know I'm very close to being out of time. Where we're going next. So we propose something called hybrid weather prediction. So we use machine learning. It's on the same grid as a climate model. How about we use the two? So previous work has really shown success in combining a numerical model with a machine learning algorithm for a spatial temporal chaotic system. And they show remarkable improvement in forecast skill compared to that of both the numerical model and the machine learning only predictions. And the goal is to develop a system that leverages both the general circulation model, or SPEEDY, and a machine learning algorithm, which I just presented, to improve the forecast by training the machine learning on the reanalysis data, which, again, I just showed. This is what the architecture ends up looking like when you do a hybrid parallel architecture. You have your U of t is your numerical model. You have your U of t, which again is your time series signal, and you put your U of t both into the numerical model to make a 1 hour forecast and into your machine learning algorithm to make a 1 hour forecast, and you get this composite state. So you have a machine learning forecast and you have a numerical forecast, and you train your W out layer to be able to leverage both the machine learning, so in areas where the machine learning does well for a 1 hour forecast, such as moisture and temperature, and to correctly weight the numerical model where it does really well, like the V component of the wind and wave dynamics. And then you put that into this composite state, and you get a hybrid forecast, which is the combination of the, again, numerical model and your machine learning. And I won't get into detail about SPEEDY, just that it's a climate model, it's a primitive equations, and some of the resolution is about 300 kilometers. But I just want to show some really quick results. These are preliminary, but we show that the hybrid is able to do better than both the numerical model and the machine learning only for every variable for the first 3 days. We still haven't, again, fixed the climate for the hybrid. We see that the hybrid ends up saturating higher, but it's definitely saturating at a lower level than that of our machine learning only, but not as well as our numerical model. So it's able to correct for a 1 hour time step, and it really does remarkably improvement. I mean, not only are you leveraging the numerical model information, but you're also leveraging the parallel machine learning only forecast information and putting it in a combination of a way that you get improved results compared to either method. So the hybrid is definitely working, although tuning a model to get the climate right is quite complicated, and we haven't been able to do that yet, but we are hoping to do that sometime during the summer, and we're really hoping to get a paper out in the next month or two about this. But with that, I'll just draw some conclusions because I know I'm really getting close to the end. Parallel machine learning architecture that we proposed is scalable. It can be done offline, as in you don't have to do this online in a operational setting. You can do this when you don't need to make forecasts on a different supercomputer and then put it onto your operational supercomputer if you wanted to. And it's quite a bit faster than that of a numerical model. It can be synchronized to make predictions at any time after being trained. So once you train it, if you trained it 2 months ago, but you want to make, and you stopped training it 2 months ago, but you want to make a prediction starting today, you can synchronize it without having to retrain it or anything. and still be able to use that trained reservoir computer to make predictions starting today, which is obviously an important thing. A data-driven only global forecast model can produce stable and realistic results with prediction skill out to at least day 3. All the variables that we showed that we used have skill out to day 3, some more, some much more actually, but 3 days is really where we start having some problems compared to that of a normal numerical model, but still quite great results for the first attempt at this. And then finally, a hybrid system similar to Peetak et al. 2018 can successfully be applied to a numerical weather prediction model. Obviously, some caveats to that is the stability issue, where we're not getting the climate right after 10 days, but those things are tuning. When you see numerical model results, they take quite a bit of tuning in terms of how to get the climate right. So we're really, in that phase of it. And with that, I really take any questions and thank you for your time.
Thank you so much, Troy. This was really quite enlightening. Very fantastic work.
Oh,
congratulations.
Thank
you. So we do have a pending question from one of our attendees. Before I go to that, I just want to quickly get your, learn from experience about this hybrid weather modeling. So it seems that you have two different approaches, the machine learning approach and the numerical approach. So are they running on the same architecture? Is there a latency between the data? So how do you get around that? Because, numerical, these things are run at different speeds, right?
Yeah, so, well, the interesting thing is, I'm going to go back to this, is the things outlined in this can take at any, so the numerical model has to run at 3 seconds or about, and if you run it any slower, you start running into problems with stability and your numerical model is going to crash. So we just, we use this as like a black box approach. We don't care what's going on inside the U of t, so we put your U of t in. It could integrate a million times for all we care. We just care about what's the output. So that 1 hour forecast. So we can, and you can do even more complicated things. You can run these in even, I don't want to even suggest how to see this without being really like understanding of how this works, but you can actually have these things that delay coordinates in terms of time. So you can really do a lot of this. We don't know what's the best way. Really, we're exploring in the dark. But these things do run at different times, and it seems that it's robust enough to understand that, and that's really speaks volumes for reservoir computing.
That's very cool, because we tried to do that in one of my research, and that was a big issue, the latency between the outputs. So coming back to one question from one of our participants, the audience. So Jordy asked this question. Okay, about your the dimensionality reduction thing you talked about, the square in the square over the grids. You had the map of the continental United States, and you had grids.
Sorry, I'm gonna go all the way back.
Yeah, this one exactly. So Jordy is asking that does this type of dimensionality reduction be helpful in looking at local or hyperlocal climates?
That's like the key here. So we're. Sure. Sorry, I didn't know if the question was finished. Sorry to jump.
No, that was it. Yeah.
Yeah, so that's really the key. So again, if I go back a couple of slides, we're talking about, can to predict the 3-dimensional atmospheric variables for the entire globe. Sure. The entire globe is not homogeneous. We have things like mountains and stuff. Even in this plot, you can see this plot of elevation and stuff. So we have, and land use. So we have things like mountains here. We have the Great Plains in a different color. Sorry. So being able to reduce the dimensionality of the problem really is key. I mean, if we tried to throw an entire, we could do something like similar to a UNet, where you have an auto encoder and a decoder, so you can use something with 1 million inputs and predict 1 million outputs, but it would be near impossible with the current, computational architecture for it to reach the part where it can understand the difference between a mountain at one grid point and farms at the other. So really the dimensionality reduction is key here. And that's how we get such great results, I believe, at least, because even the difference between, at this resolution, the difference between some of these grid points is really vast. Here we're going from maybe 2,000 meters, or, well, I guess the Rockies aren't that tall, but, maybe they are. I don't know how tall the Rockies are, to, the Great Plains over the course of a few grid points. And, I don't believe that a UNet type architecture or even a convolutional neural network would be able to express that as well, because it would just be overwhelmed with the data that it's getting inputted.
Yeah, that makes sense. So yeah, that was all the questions, and I think we're a bit over time. So
Yes, I
let it be
apologize.
now. But this was fantastic, Troy. I think this was a
Thank you.
very enlightening talk. I'm sure our audience enjoyed this. Thank you so much for joining us, all of
Yes,
you.
thank you.
I hope you have a great evening wherever you are, and stay safe. Thank you, Troy. Yep.
Thank you so much.